your session chair for this session today, the first of two on UAVs. It's my pleasure to welcome Kamak Ebadi, who will be speaking about robot localization in the Mars helicopter scenario.
Hello everyone, my name is Kamak Ebadi. I'm a doctoral research fellow at NASA Jet Propulsion Laboratory, and today I will be presenting the result of our experimental study for localization of a Mars rover in Mars helicopter aerial maps. So the past and present Mars missions have been location-oriented missions, which means that the rover needs to stay in one area for an extended period of time to study the habitability and geology of an environment. In contrast, the future Mars missions are going to be more drive-oriented missions, meaning that one of the main objectives is to go to different locations on Mars and collect a diverse set of samples for subsequent return to Earth. So traversing a longer distance on Mars requires a better and more robust autonomy solutions. So autonomous vision-based navigation on Mars has been a challenging problem because, as you see on Mars, we're dealing with situations like this. On one side, we are dealing with a terrain that is what we call like feature poor. You can hardly detect any salient features from the left side. And on the other side, you have a feature-rich environment that you can use those features for autonomous navigation and visual odometry. So the current solution to this problem is human intervention by manually pointing the mast toward the feature-rich area and obtain images that can be used for visual odometry and vision-based navigation. We've been working on a perception-aware mast pointing solution. So this approach would enable the rover to learn autonomously and decide autonomously where to look and where to point its mast to get pictures that can reduce the uncertainty and visual odometry failure. So here's how the perception-aware mast pointing works. At time step K, the rover obtains a measurement of the environment, and let's assume we can consider two action candidates for the rover, A0 and A1. Before the rover takes either of these actions, we can predict what the rover would see if it took either of these actions, and we can create synthetic images to show what the rover would see if it took either of these actions. So what you see there is the prediction image. It's a synthetic image created from the measurement ZK, and then we can compute a cost for that action A0 and A1. So a cost can be defined as a drift in visual odometry, for example. So you see the two actions here is action A0 and action A1. In action A0, the rover would move forward while pointing the mast looking forward. So this is what the rover would see, and you can see there are only few features detected here. However, if the rover chooses action A1, it will move forward while pointing the camera to the right side, and you see we have a lot of good features in here. So there are a lot of strong features have been detected that can improve the visual odometry performance. So obviously the cost of action A0 is a lot larger than cost of the action A1. So here's an example of generating synthesized images and predicting what the rover would see. So at time step K, we have obtained one measurement, and from this one single image, we can create a sequence of synthetic images predicting what the rover would see if it took the action A1. So I need to emphasize here that the rover is not moving, the rover is still stationary, but predicting what it would see, and then based on that prediction, we can see if this action and what the rover would see would improve the visual odometry performance or not. So perception-aware mast pointing is able to reduce the uncertainty and the visual odometry failure, which is great. However, because it relies on the rover's measurement and it's basically limited by rover's onboard camera, field of view, and the range of that camera, so we cannot basically use it for a long-term strategic planning. We can only predict a few steps in the future. So a potential future solution for this is the Mars helicopter. So NASA is planning to launch a helicopter to Mars in 2020. On a good day on Mars, it can fly for 90 seconds, a range of 600 meters, and altitudes ranging from 3 meters to 10 meters. So the main objectives for the Mars helicopter is to identify interesting science targets on Mars and also acquiring high-resolution aerial imagery. So once the aerial imagery are acquired by the helicopter, a high-resolution aerial map can be created, and provide it to the rover, so now the rover can use that aerial map for long-term strategic planning. However, the challenge is, before the rover can use that aerial map for long-term planning, it first needs to establish its own position within the provided map so it can rely on it for long-term planning. So this is essentially an aerial to ground localization problem, where the rover needs to establish its location by acquiring ground images and registering them to the aerial imagery. So here's, I'm going to explain to you how the aerial to ground localization process works. So from the sequence of aerial imagery obtained by Mars helicopter, we can extract the image features. It could be any type of feature, so it's agnostic to the type of feature detector descriptor we're using. And then we can estimate the camera poses and recover the 3D structure of the terrain. So what you see here is a 3D reconstruction of a portion of the JPL's Mars yard from the aerial imagery. And as you can see, the locations of the camera for each of the aerial images are estimated, and we show that with gamma I. So once the aerial map is created, it is provided to the rover, and the rover now needs to establish its location within the provided map. So at time step K, rover obtains a measurement. From that measurement, we extract the features, and then we rely on methods based on fast library for approximate nearest neighbor search to search in the feature descriptor domain for the closest neighbors to the features extracted from rover's measurement. On top of that, we apply ransack to reduce the number of outliers. However, in a Mars-like environment, because of the high degree of perceptual similarity between different scenes, and because it's an unstructured and ambiguous environment, we deal with situations like this. So on the left side, you see the rover's query image. So this is the same image on the left side. And on the right side, you see that after applying FLAN and ransack, the query image ZK is matched to multiple aerial images, where each aerial image is corresponding to a different location on the aerial map. So here, from image matching, we are not able to correctly estimate the position of the rover because we have ambiguity in data association in this case. So what we can do here is to measure the degree of similarity between the rover's observation and those aerial images, and to come up with a metric to evaluate that similarity. We, for a set of corresponding points in rover's image and an aerial image, we project the corresponding points in the aerial image to the rover's image, and then we measure the residual error. So which you see is the average residual error between the reprojected points and the rover's points. And we use that error as to come up with a similarity score. So if the error is a very large number, we get a similarity close to 0. If the error is a small number, we get a similarity close to 1. And we also remember that in the previous step, when we were constructing the aerial map, we were able to estimate the camera location for each aerial image. So for aerial image AI, I have an estimated camera location, gamma I. So the similarity of rover's measurement to image AI, we can also write it as a likelihood of getting that measurement of rover at location gamma I in the map. So it would give us a likelihood of, like, what is the likelihood of getting that measurement in a certain location in the aerial map. So once we have that, we will use a particle filter localization approach in order to estimate the position of the rover within the map. So at time step 0, you can see that the belief of the rover, which is the probability over all possible locations of the rover on the map, is represented by a finite set of particles. So the blue dots represent the particles, and this is the rover's true position based on the ground truth data. And at time step 0, because we don't have any prior information about the location of the rover, the particles are uniformly distributed over the entire map. So once we obtain, so in the prediction step, the particles are moved based on rover's action model, or the motion that we have commanded the rover to take. And in order to update the weight of the particles, we would rely on the likelihood that we obtained in the previous step. So assume that these are the estimated camera locations on the map. So because we have a sparse set of estimated camera locations on the map, but the particles are covering the entire map, for each particle we look for the closest estimated camera location, and then we use the likelihood that we obtained here to update the weight of each particle, and that's how the particles are being evolved. So you see here, after taking few images, the particles are now converged into 4 different locations on the map, and these are, by the way, the same 4 locations that I showed you that we had that ambiguity. And through this recursive process, we are able to reduce the hypothesis, and eventually all the particles are converged on the true location of the rover on the map. So in order to run experiments, we did our experimentations at Jet Propulsion Laboratories Mars Yard, which is an outdoor simulated Mars-like environment. And our main objectives was to study the A2G localization performance in different terrain types, varying viewing angles, illuminations, and using different feature detectors and descriptors. So in the Mars Yard, we created 3 different types of environment: feature-rich, feature-poor, and an environment which is texture-rich, but it's ambiguous because you don't see any distinctive landmarks, so we consider that as a repetitive feature. So you can see the environments that we have created as a top view of JPL's Mars Yard. So one of the things we were interested to study was the viewing angle variations between the aerial and ground imagery, because that's one of the main challenges when you want to do a ground-to-air registration. So we obtained multiple images at different viewing angles and compared the performance of aerial-to-ground image matching with a reference image, and our metric was basically the number of extracted features, matched features, and the number of inlier features. So this information not only basically for the perception-aware mass pointing that I mentioned to you, where to look to be able to extract more features, we also want to know not only where to look, but how to look, in what angle to look, so that we can improve the localization performance. And here, as you can see, at 35 degrees viewing angle difference between aerial and ground images, we can get a very good number of inlier points, but beyond that, there is a rapid decline. So this could inform our perception-aware autonomy solution to point the mass in a better direction. So here you can see the localization in a feature-rich terrain. The viewing angle between aerial and ground was kept at 35 degrees. And using different feature descriptors and detectors, we were able to localize the rover in all of these cases. However, because SURF and SIFT, they provide the largest number of basically inlier points, you can see that the algorithm was able to converge much faster and localization was achieved much faster. We also tested our algorithm in different terrain types to see how the rover would perform in terms of localizing itself in the aerial map. So in feature-rich, feature-poor, and ambiguous environment, we've only used surf features in this experiment, and the experiment was done in the morning, so the same time of day, no variations in the illumination condition. And as you can see, when the rover is looking at the feature-rich area, we're able to reduce the localization error almost to 0. However, in feature-poor and repetitive and ambiguous environment, because of the ambiguity and because of lack of any distinctive landmarks, we're not really able to reduce the localization error significantly. So that shows the importance of the perception-aware algorithm, so the rover knows where to point its mass and at what angle to point its mass in order to reduce the localization error. This is an experiment for illumination variations. So the aerial image data set by the Mars helicopter was collected at 9 a.m. in the morning. However, we had 3 ground data sets at 9 a.m., 1 p.m., and 5 p.m. So different illumination and shadows. In Mars Yard, we relied on surf images descriptor and detector. And as you can see, again, in feature-rich area, despite significant variations in lighting and shadows, we're still able to obtain localization. But in the feature-poor and repetitive feature environments, we are not able to reduce the localization error significantly. So the conclusion is the aerial to ground localization in unstructured Mars-like environment is extremely challenging because it's an ambiguous environment with no sparse, with no salient or distinctive landmarks, and high degree of perceptual similarity between different scenes. However, when we use perception-aware mass pointing to point the mass toward a feature-rich area, and knowing the angle that works best and the feature detector descriptors that works best, we are able to obtain localization using a aerial-to-ground image matching embedded with a particle filtering approach. So once the location of the rover is established within the provided aerial map, now we can basically work on coming up with a long-term strategic planning for the rover. So what you see here, this is an image obtained from the helicopter. So this is an aerial map, But once the rover is localized within this aerial map, now we can create these synthetic images, predicting what the rover would see for an extended period of time and planning a path for the rover based on that aerial imagery. So with that, I would like to close the talk, and I would be happy to answer questions. Thank you.